so let's solve this. So if you can, however you want to do it, you can look at Wolfram alpha, for example, and you will see that there are two eigenpairs. One is eigenvalue -2 and eigenvector 2, 3, and the other one is eigenvalue 1 and -1 and eigenvector 1, 1. So the general solution then is x1 of t. x2 of t is equal to a times e to the minus 2t times 2, 3 plus b e to the minus t times 1, 1. And let's go on ahead and plot the phase diagram for this, or the phase portrait. So remember, we're going to look at this in the x1, x2 plane. This is x1, this is x2. So I'll look at, I'll plot the eigenvector solutions first. So I'll do, this one will be green. Okay, so 2, 3, sorry, let me make a few little marks here. So 1, 2, 3, 4, 1, 2, 3. Okay, so 2, 3 looks like it would, 2, 3 looks like it would be like this. Okay, and so if a solution starts on this line, as t goes to infinity, it's going to go to the origin, because the magnitude of this vector goes to 0 as t goes to infinity, and it goes to infinity as t goes to negative infinity. Okay, but the arrows are for the direction of increasing t. Okay, now for the blue vector, or sorry, for the red vector, sorry, for the other vector I'll use blue. Wow, and it looks like my scale is kind of off a little bit, so let me redraw the green vector. So 2, 3 is going to be like this. And now I'll do the other one. Oops. So 1, 1 is going to be like this. Okay, I didn't quite go through it, but that's fine. Oops, didn't mean to draw the arrow there. Okay, obviously when you're hand drawing these things, the scale is always going to be wrong. Okay, so if a solution starts here on the red line, then as t goes to infinity, the magnitude goes to 0, so the solutions also go in like that. Okay, so now remember, how do we get the rest of them? How do we draw the phase portrait for, say, a solution that starts here? Okay, well, for very big positive values of t, both the green vector and the red vector are going to be small. But the red vector is going to be, the green vector is going to be even smaller, because e to the minus 2t gets very, very small as t gets bigger, and e to the minus t gets very, very small as t gets bigger, and e to the minus 2t is getting smaller faster. So what this means is that for very large values of t, the red vector is going to be the dominant vector. Okay, and not only that, since the solutions are all going to 0, solutions are going to get closer and closer to that vector. And for very big negative values of t, well, we've got e to the 2t, or e to the minus 2t, and e to the minus t. Well, again, for very big negative values of t, both of those are going to be really big, but e to the minus 2t is going to be even bigger if t is negative. And so those solutions are going to be parallel to the green vector. That's going to be the dominant vector. So it's going to look something along these lines. Okay, and so we're going to look at vector. The vectors are going to look something like this, or the solution trajectories are going to look something like this. Okay, now it's important they don't get closer. They do not get closer and closer to the green vector as t goes to minus infinity. They just become more and more parallel to the green vector. Okay, and so if something starts here at negative infinity, it'll be parallel to the green vector, and then as it comes in, it's going to get closer and closer to the red vector. Okay, and so similarly, if you have something out here, for very big negative values of t, it'll be parallel, and then it'll sort of zoom in like this as t goes to infinity. Okay, and so this is a sketch of the phase diagram.